Remember what E is? Energy, right? E is energy. What kind of energy? E is the internal energy, the sum of the energy of all kinds for a system. So systems exchange energy with their surroundings. And we can look at the change in energy. So here we have a system, here we have the surroundings, and there are two means by which energy can be exchanged. One is heat. Heat is the flow of thermal energy due to a difference in temperature. And the other is work. So we're going to be talking about gases when we talk about this sort of pressure volume work. So the system and the surroundings, we can have an exchange of energy via heat and work. And they could be both positive, both negative, one positive, etc. All possibilities. So the change in internal energy, delta E, is the measure of all the energy that's exchanged between the system and the surroundings. So it's the heat plus the work. So delta E, the change in energy, is equal to Q plus W. Now, if there's no change in volume, W is 0. Right? Because what was W? W equals negative P delta V. Well, if delta V is 0, then W is 0, right? So if there's no change in volume, W is 0, and then this is much simpler. The change in energy is equal to the heat exchanged. And we put a subscript V here to indicate this is heat at constant volume. So when the volume doesn't change, we don't have to worry about the work. Well, it's not practical to observe the temperature changes of the chemicals in a reaction because they're like, an aqueous reaction. They're all mixed together, and how do you measure the temperature of one versus the other? You can't. But we can measure the amount of heat that is exchanged between that reaction mixture and the surroundings. And we do that using a controlled situation, and one way to do that is called a bomb calorimeter. I'll come back to this slide, but let's look at the picture here. So this is an illustration of a bomb calorimeter, and it doesn't explode. So what we have inside is we have this little sealed, they call this the bomb, and you've got your sample in here. This is often used for measuring heat of combustion. So you've got your sample in here, you've got plenty of oxygen in here, you have an ignition source so that you can give it a spark and set it burning. And this is airtight, so the volume can't change, and it's submerged in water. And the water will absorb the heat that's given off by the reaction. We've got a thermometer in here so we can measure the temperature, and then we've got a means of stirring this so that we can have that heat get dispersed and have the water be a uniform temperature. The outside of this is well insulated so that we don't lose heat to this even more larger surroundings. So we measure the temperature change in the liquid surrounding the bomb. We can measure that pretty easily. It's hard to measure the temperature of the stuff going on inside that bomb. So Q for the system is going to be opposite in sign to Q for the surroundings. So whatever energy is released by that chemical combustion reaction inside the bomb, that energy has to be transferred to the surroundings. And we're controlling the surroundings so that we can measure the temperature change. So the surroundings is the calorimeter. And so the Q for the system is equal to Q for the calorimeter. It's just opposite in sign, because one lost energy and one gained energy. And so this is called calorimetry, literally measuring calories. It's a technique used to measure the heat of a reaction by observing the change in temperature of the surroundings. So we've got the system, which is our chemical reaction. We've got the surroundings, which are generally going to be the calorimeter. And we're going to look at the temperature change here, and that'll allow us to calculate the amount of heat that was released. Oops. This is where I want to be. So Q equals MC delta T, right? So Q for the calorimeter, excuse me, is equal to a heat capacity. This isn't the specific heat capacity, this is just the heat capacity. It's MC, it's got the mass combined in there because the mass of the calorimeter doesn't change. So we've got the specific heat of the calorimeter times the change in temperature. So we're measuring the temperature change in the water. And that will be equal to the amount of heat released by the reaction inside. So Q for the reaction, because this is a constant volume, is equal to QV, and QV is equal to delta E for the reaction. So it's a change in internal energy of the reaction. Any questions? The very important concept to grasp here is we're looking at a chemical reaction occurring in here, and then we're looking at the calorimeter here as the surroundings, because this is well insulated, and so we can assume that there's no loss of energy into the further surroundings. Technically, the rest of the universe is the surroundings, but we've put this thermal barrier here, so we just have to look at what's the temperature change of the water. The heat lost by the reaction is gained by the water. That's the important concept there. Okay, let's do a problem. When 1.550 grams of liquid hexane undergoes combustion in a bomb calorimeter, the temperature rises from 25.87 degrees C to 38.13 degrees C. Find delta E reaction for the reaction in kilojoules per mole of hexane. The heat capacity of the bomb calorimeter determined in a separate experiment is 5.73 kilojoules per degree Celsius. So what we have here is we have the hexane combusting, that's the reaction, that's going to release energy, and we have the calorimeter absorbing the energy. So Q for the reaction equals negative Q for the calorimeter. The heat lost by the reaction equals the heat gained by the calorimeter. Well, Q equals MC delta T, right? So let's just remind ourselves of that. Q equals MC delta T. Well, we don't know much about the reaction. We don't know its specific heat capacity. We don't know its change in temperature. We're looking at the change in temperature for the calorimeter. This heat capacity for the calorimeter is actually MCS. The specific heat capacity, this should be S up here. And we just call that C for the calorimeter. So Q for the calorimeter equals C for the calorimeter times the change in temperature. What's the change in temperature? 12.26. Well, I can't do that math in my head. 38.13 minus 25.87. I think you're right, but it's too early on a Monday morning. That's why we have calculators, right? Yes, 12.26. If I had a gold star, I would give it to you. So that's the change in temperature. So Q reaction equals negative Q cal, so that's negative C cal delta T. Well, we know what C cal is. Actually, let's not do it right there, because they gave that to us. We still need that negative sign in there. 5.73 kilojoules. Write this as a vertical fraction so that you see that degree C is in the denominator. And that's times delta T, which we figured out was 12.26. And then when we look at the units, the temperature cancels out. So minus 5.73 times 12.26, negative 70.249 kilojoules. Is that the answer? Not quite. What units are they asking for? Kilojoules per mole of hexane. This is the amount of energy released by 1.550 grams of hexane burning. So, it's nice to be able to figure that out. It's not very useful because it's specific to this one situation. If we knew how much energy was released per mole, then we could use that in other calculations. If we had 5 moles or 0.7 moles or whatever, we could calculate the energy. So to get kilojoules per mole, we're going to divide by moles. Well, how many moles of hexane do we have? We don't know, but we can calculate it, right? So we need the molar mass of hexane. So we've got 6 times 12.01 plus 14 times 1.008. Um, 86.172 grams per mole of hexane. So we've got 1.550 grams of hexane. So we can multiply by moles over grams, and it's 86.172 grams per 1 mole of hexane. Okay, there's just not enough room there. 0.0179. I need 3 sig figs here. Actually, I need 4 sig figs. Take that back. 1798. There's 4 sig figs. Carry 2 extras. 72 moles. So the heat of reaction is equal to the amount of energy released divided by the moles of hexane. So I've got negative 70.249 divided by 0.0179872. I get minus 3905.4. How do I round that? Is it minus 391? No, not even close. It's minus 3,910. I could round it that way. Or scientific notation is better. We're going to move the decimal point over here 3 places, and then we don't have to worry about putting in placeholder zeros. 3.91 times 10 to the 3rd kilojoules per mole. I would rather have the wrong number of significant figures than the correct number rounded incorrectly. You round it and change the number, it's really bad. Any questions? Yes?
In the beginning of the integrated Q R X N,
Mm-hmm.
Q cal,
Yes.
and then that is also equal to negative C cal in the temperature.
Mm-hmm.
Isn't the Q of R X N like 12.264, am I getting that?
You might be thinking ahead to constant pressure calorimetry. So we're not able to measure the temperature change for the reaction inside the bomb. So all we can measure is the temperature change of the surroundings. And so on the right side here, Q cal is equal to C cal delta T. And so I'm just substituting this in here. Does that help?
Yeah.
There are a lot of things in science that we can't observe directly. And so we observe them indirectly. I can't tell how much energy is being released by this reaction, but I can set it up so that I can monitor how much energy is being absorbed by the surroundings. And that has to equal what was released by the reaction. Any other questions?